Today I'm going to show you a cool trick using Pythagoras' theorem, so that's a squared plus b squared equals c squared. This trick means that you can come up with your own Pythagorean triples really quickly and easily. Let's have a look at some examples first and we'll see where this idea comes from. So the most famous Pythagorean triple, of course, 3 squared plus 4 squared equals 5 squared. Quickly on to our next one. 5 squared plus 12 squared equals 13 squared. That one's also really famous. But one that's slightly less well known, we've got 7 squared plus 24 squared equals 25 squared. One that's less well known again would be this. We've got 9 squared plus 40 squared equals 41 squared. Let's go for one more so we can really see this pattern. 11 squared plus 60 squared equals 61 squared. Well, so far what have we seen? These are all valid Pythagorean triples. They actually work. But let's consider the pattern that we've got here. If you look at the first number in each row, these are just a sequence of the odd numbers. And this is really how this trick works. If you take any odd number, so we've taken 3 in this one, and you square it, so 3 squared is 9, and 9 is made up of 4 plus 5. We always want consecutive numbers. This one works the exact same. We take 5 squared, that's 25, and 25, 5 squared, is made up of 12 plus 13. The same two numbers we see in our triple. Likewise with 7 squared. 7 squared is 49, and 49 is made up of 24 plus 25. Let's just whiz through the other ones so we also see those. Well, 9 squared is 81, and that's made up of 40 plus 41, and 11 squared is 121, that's made up of 60 plus 61. Can you see it's the same 3 numbers each time? So the real way that this idea works is you take any odd number, you square it, you find the 2 consecutive numbers that add up to that square, and those 3 numbers make a Pythagorean triple. This will go on forever, and now we're going to prove that that's actually the case. First of all, to prove it then, let's draw a picture to think about what we want to show. So again, we've got a right angled triangle, so it follows Pythagoras. The first side to consider is the side that has to be the odd number. And if you're familiar with these kind of proofs, an odd number must be 2n plus 1. Well, let's think what happens when we square that 2n plus 1. If we take 2n plus 1 and we square it, we're going to get 4n squared plus 4n plus 1. What we're interested in though is the 2 consecutive numbers that add up to that 4n squared plus 4n plus 1. And those 2 numbers must be, with a little bit of consideration, 2n squared plus 2n, and the other one must be 2n squared plus 2n plus 1. Luckily for us, that plus 1 on the end of here did us a real favour, because that's the only difference between this number, 2n squared plus 2n, and this number, 2n squared plus 2n plus 1. Filling out our diagram then, this 2n squared plus 2n, as the smaller of these two, must be this side. So let's add that in. 2n squared plus 2n And the 2n squared plus 2n plus 1, this has to be the hypotenuse. It's the largest of the three sides. So 2n squared plus 2n plus 1. What we'd like to do now then is actually run through Pythagoras' theorem with these three sides to check that it works. First of all, let's do this one and this one. We need to square them, add them up, and check that they add up to make this thing. But we'll call these two our left-hand side. So let's start off left-hand side. Well, we start off with 2n plus 1. So 2n plus 1 squared. And we would like to add to that 2n squared plus 2n and square that. So 2n squared plus 2n squared. This should be a nice bracket sign. Working through it then, well, 2n plus 1 squared, that gives us 4n squared plus 4n plus 1, and 2n squared plus 2n all squared is going to give us 4n to the power of 4 plus 8n cubed plus 4n squared. But what we need to do now is add all of these up. Let's just simplify this a bit. We've got 4n to the power of 4, that's our largest term. So 4n to the power of 4. If we look at our cubed term, it's just the an cubed. So plus 8n cubed. If we look at some square terms, oh, we've actually got two of those, 4n squared and another 4n squared. So we want to add 8n squared. We've just got one n term, that's the plus 4n here. So plus 4n and then a plus 1 on the end. A bit neater. 4n to the power of 4, 8n cubed, 8n squared, 4n plus 1. Okay, that's our left-hand side. That's these two squared and added. What we'd like to try now is our right-hand side. The right-hand side is a bit more horrible because we've got to expand this, square that bracket. It's got three things inside. Let's do grid method to make it look a little bit nicer. So we've got 2n squared plus 2n plus 1, and we want to times it with itself. 2n squared plus 2n plus 1 expanding it with a grid like this just to keep us on track. 2n squared times 2n squared will give us 4n to the power of 4. 2n squared times plus 2n will give us 4n cubed, and here we'll get plus 2n squared. Here we'll get 4n cubed plus 2n times plus 2n gives us a plus, let me keep my plus signs for being neat, plus 4n squared and a plus 2n here. We'll get 2n squared in this box, a plus 2n here, and then lastly over here we'll get plus 1. Remember, in the grid method, diagonal boxes, so 1, 2, will always add up together. They'll be like terms. So these three will all add up. Let's add up what we've got. Just a 4n to the power of 4. If we look at our cube terms, 4n cubed plus 4n cubed gives us plus 8n cubed. Now let's look at our square terms. 1 is plus 2, plus 4, and another plus 2. Great, that's plus 8n squared. Just our normal n terms, plus 2n and plus 2n gives us plus 4n. And lastly, a plus 1 on the end. We don't have to be super observant to notice that this our left-hand side and this are equal to each other. What that means is that if a squared plus b squared are equal to c squared, we're following Pythagoras' theorem. That means that this must hold in general. So we've actually proved what we wanted to prove. We could say the left-hand side equals the right-hand side. We've proved it. Going forward then, that means for us, we can take any odd number. So if we'd like to choose a more creative one, like say 15, we know 15 squared is 225. Thinking of the two consecutive numbers that add up to that, we've got 112 and 113. So these three will necessarily form a Pythagorean triple with each other. In other words, 15 squared plus 112 squared equals 113 squared. I don't need to work that out on my calculator because I've just proved it.